Okay, so this is lecture notes 3 for Math 113. This is covers sections 4.5 and 4.6 in the book, and keep in mind that the book is part of your subscription to my math lab. You can find it in the online section. So what we want to do is graph the trig functions, right? Graphs of trig functions. So we'll start with sine x. So how do we get the graph of y equals sine x from the unit circle? So we have to remember that sine x, right? If I'm going to start calling this angle x, sine of x is the y coordinate. So can we put together a little table? X, y equals sine of x. So if we have an angle of 0, sine is 0. If we have an angle of pi over 2, that's a right angle here. And sine is 1 because our y coordinate is way up here. An angle of pi brings me to this point, and my sine is, and sine of pi is 0. 3 pi over 2, that's down the y-axis to minus 1. And then if we come all the way around the circle back to 2 pi, that brings us back out to x this point, and that is at 2 pi, we have sine equal to 0. So we've got our nice little table, sine, and so we can graph them. These are our 5 special points on the graph. 0, 2 pi, halfway along is pi, halfway there is pi over 2, and if we cut this one in half, we get 3 pi over 2. And this is my x-axis, this is my y-axis. Maximum number we get here is 1. Minimum number we get here is minus 1. So this could be minus 1. At 0, we're at 0. At pi over 2, we're at plus 1, 0, minus 1, and then back to 0. So those are my 5 points graphed. And that gives me the graph of the function. And this is one cycle, right? We're just going from 0 to 2 pi. But what does it look like if we continue that? Well, we went around a circle once is 2 pi, that brought us back to here. And notice every time I go around the circle from 0 to 2 pi, my sine values come back to the same thing. So if I went around once, that'll get me to 2 pi, plus another 90 degrees would get me to 5 pi over 2, but that would give me 1 because that's 2 pi away from pi over 2. So what does the graph look like of sine? It repeats every 2 pi, and that's its period, because once around the circle is 2 pi radians. So our basic period is 0 to 2 pi, cut it in half, cut it into fourths, and we go 0, positive, 0, negative, 0. Right? Plus 1, minus 1, and that's 0. So if we go out to 4 pi, we cut the chunk between 2 pi and 4 pi in half, cut that in half again. 0, positive, 0, negative, 0. And we just get another copy of the curve. If we go negative, negative 2 pi, we can cut that in half, cut that in half, cut that in half. Going backwards, though, we'll go negative, positive, no, negative 0, positive 0. Down and then up and then down. So it's the same pattern over and over again. Reading from left to right, 0, positive, 0, negative, positive. 0, negative, 0, God, I can't, it's so hard to get this right. 0, positive, 0, negative, 0. And then you just repeat that cycle. So what are the 5 special points on the graph of y equals sine x? Just to pick these out. 0 to 2 pi. Cut the graph in half, that's at pi. Cut the half in graph, cut the interval in half again, pi over 2. Cut this one in half, you get 3 pi over 2. Positive 1, negative 1, 0, positive, 0, negative, 0. That's the basic cycle of cosine. So that gives us the basic properties of the graph of y equals sine x. The domain is all reals. The range is -1 to 1, right? Because we only go up and down. Range is up and down again. So -1 to 1, or in interval notation, square brackets, because we actually do get down to -1 to 1. Period is 2 pi. It repeats every 2 pi. It's the same pattern every 2 pi units. It's an odd function. So if we go back and look at this, right, a point here, if you reflect it through the origin, you get that. So odd function. And there's these 5 special points. 0, 0, that's here. Pi over 2, 1, that's here. Pi 0, 3 pi over 2 minus 1, 2 pi. Okay. So we want to be able to modify the graph of y equals sine x to y equals a times sine bx plus c, because there's a lot of complicated periodic phenomena that aren't just straight up sine graphs. So we'll first look at what a does, and then what b does, and then finally what the c does in this graph. So what does the a do in the graph of a sine x? Well, if you remember from algebra, multiplying a function by a constant just stretches it towards the x-axis. So let's get your graph of y equals 5 sine x. We'll start with our basic cycle, which is 0 to 2 pi, pi over 2, 3 pi over 2. And one of the reasons why I want people to write out these notes by hand is because the more often you draw this graph, the better you'll be at remembering it. So there's the basic cycle. Remember, that's 1 to -1. So what does 5 sine x do? Well, our basic graph, x, y equals sine x, 0, pi over 2, pi, 3 pi over 2, 2 pi. Those are our basic points. What are the y values? 0, positive, 0, negative, 0. So y equals 5 times sine x means take these y values that you calculated by putting your x into sine and multiply them by 5. So 0, 5, 0, -5, 0. So what does the graph of y equals 5 sine x look like? So we'll go from 0 to 2 pi again. The same process of setting up our points. Divide it in half, divide it in half, divide it in half. This is pi over 2. This is pi. This is 3 pi over 2. We get the same shape. It's just that now instead of going from 1 to -1, we're going from 5 to -5. So it looks exactly the same. It's just been stretched out, right? The basic sine graph is from 1 to -1, but we've stretched out to 5 to -5. Okay, so it's called the amplitude, and it's just how high up and down away from the x-axis that your graph goes. What does b do? It is the frequency. It's how many cycles you fit into 2 pi. So y equals 2 sine 3x. We know what the 2 does. So 2 is the amplitude. It's going to stretch our function away from the x-axis. Let me just check and see plenty of space down there. Okay, so y equals 2 sine x. Here's 0. Oops. Here's 0. 2 pi. Fill in the corner points. We'll have point there, point here, point here, point here, point here. My graph goes like this. Amplitude means that I'm going from 2 to -2. That's what the A does. That's what this 2 does. But what does the 3 do? So the 3 is the frequency. What that means is that in the space from 0 to 2 pi, we want to fit in 3 cycles instead of just 1, right? It's moving 3 times as fast. So when we think of y equals 2 sine x, and that's this graph here, one period is up to 2 pi. But y equals 2 sine 3x, one period is, well, if I replace the x with the 3x here, I've got to replace this x also by a 3x. Or if you divide all 3 sides by 3, it's 0 to 2 pi over 3. So we have one cycle from 0 to 2 pi over 3. And so now if I graph y equals 2 sine 3x, and I'll put my origin sort of in the middle here. This is my origin 0. It's going to look a lot the same, except the numbers will be a little bit different. So I'm going to 2 pi over 3. And remember that our amplitude is 2, so it's from +2 to -2. Do the same procedure. Cut this in half, cut this in half, cut this in half. 0, positive, 0, negative, 0, and draw in a cycle. So that's what it looks like. What points do we have? Well, this is halfway between 0 and 2 pi over 3. So this is going to be 2 pi over 3 over 2, which is pi over 3. What's this point going to be? It's halfway between 0 and pi over 3. So that's going to be pi over 6. So a quarter is pi over 6. So I can count by pi's over 6's. This is pi over 6. This is 2 pi over 6. That's pi over 3. This point here, that's going to be x is 3 pi over 6. That's pi over 2. And then this is 4 pi over 6. If you simplify that, you get 2 pi over 3. Great. What's the rest of it look like? Well, this is a cycle from 0 to 2 pi over 3. If we go out to 4 pi over 3, right? The cycle length is 2 pi over 3. So 2 pi over 3 plus another 2 pi over 3 is 4 pi over 3. We get the same cycle again. 0, positive, 0, negative, 0. Up, down, and up. What points are these? Well, we're still counting by pi over 6. So this point here is x is 5 pi over 6. This is 6 pi over 6, which is the same thing as pi. 7 pi over 6. Then 8 pi over 6. And 8 pi over 6 is 4 pi over 3 if you simplify it. So if we add one more 2 pi over 3, because that's the length of my cycle to this, right? Length of cycle is 2 pi over 3. You get 6 pi over 3, and that's in fact 2 pi. Cut that in half, cut that in half, cut that in half. Positive, 0, negative, 0, up, down, up. So from 0 to 2 pi, we have 3 cycles. And because it's periodic, up, down, up. It just repeats to the left and the right. Cut in half, cut in half, cut in half, up, down, up. Oh, those are supposed to come together. Up, down, up. Halfway, 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 etc. And so there's the graph of that. So 3x means 3 cycles and 2 pi. Okay, what does the C do in that graph? So C and B together give you the phase shift. So if we've got a graph of y equals 1/2 sine 5 pi over x, what do we know already? Amplitude A is 1/2. Frequency five cycles in 2 pi. But now the question is what is this pi over 3 doing? Well, we'll do the same kind of thing we did above. Remember that y equals sine x. Has a period from 0 to 2 pi, 0 less than equal to x less than equal to 2 pi. So y equals sine of 5x minus pi over 3 has a period of 0 less than equal to 5x minus pi over 3 less than equal to 2 pi. That's supposed to be an x there. Okay, so I'm going to solve for x by adding a pi over 3 to the left side and the right side and the middle side, and that means that pi over 3 in the middle goes away. And then I'm going to divide all 3 sides, the left side, the middle, and the right, by 5. So we get that. So what is that telling me? That's telling me that the period starts at pi over 15, and it goes to, so we start the cycle here, we end the cycle here. So it's 2 pi over 5 to the right of pi over 15. So, and our amplitude is 1/2. So what is the graph of this going to look like? This is 1/2 sine 5x minus pi over 3. And we have this information here about our cycle. So we start with an x-axis and a y-axis, x-axis, y-axis. We start the cycle at pi over 15, wherever that might be. And we end it at 2 pi over 5 plus pi over 15. And we'll put that over here. 2 pi over 5 plus pi over 15. What does the graph look like in between? Well, we cut this in half, cut this in half, cut this in half. 0, positive, 0, negative, positive, 0. It's the same cycle. What's my amplitude? The amplitude is 1/2. So instead of plus or minus 1, we're going to have plus or minus 1/2. We start here and we just sketch that out. So this length here of one cycle is 2 pi over 5. So if we want another one, we'll go to 4 pi over 5 plus pi over 15. 1, 2, 3, right? Those are our points. Positive, 0, negative, 0, up, down, up. And there's our cycle again. And if you keep going, it just keeps doing that. And 5 cycles later, you get to 2 pi. 5 cycles later, you get to 2 pi plus pi over 15. and that'll take you from here to here, and you'll have 5 cycles in there. And the graph continues back this way. Sine graphs all look the same. You just have to figure out where those 5 special points are and how they get mapped. And so there's a graph of 1/2 sine 5x minus pi over 3. You can try and figure out exactly what these numbers are. Right? So 1, 2, 3, 4. If the length is 2 pi over 5, a quarter of that length, right, is 2 pi over 20, which is pi over 10. So this is pi over 15. This will be pi over 10 plus pi over 15. This will be 2 pi over 10 plus pi over 15, etc. That's really not hugely useful, but you can calculate it out. So what does adding a constant do to the graph of y equals a sine bx plus c? Well, it moves it up and down, right? So if we add a 2, what's that going to do to my graph? That's going to move it up 2 units. So this is the graph. This is the function from the last graph. How do we find that graph? How do we find this graph? We take the thing inside the sine, and we put it into this inequality. We add a pi over 3 to all 3 sides, the left, the right, and the middle. And that gives us pi over 3 is less than or equal to 5x, less than or equal to 2 pi over 3, 2 pi plus pi over 3. Personally, I don't turn that into one thing, because this is the length of the cycle, and this is the shift from the pi over 3. And now we divide by 5, so we get pi over 15 less than or equal to x, less than or equal to 2 pi over 5 plus pi over 15. This number is the length of my cycle. This number, it's the same number, is the shift. It's actually called the phase shift. So that's the length of one period. So what kind of a graph did we get? Like we saw before, my amplitude is 1/2. So we went from 1/2 to minus 1/2. We started at pi over 15. We got one cycle to go from x equals pi over 15 to 2 pi over 5 plus pi over 15. And we cut that into 4. Positive there, a negative here, up, down, up. That was one basic cycle, and then it repeats. What is the plus 2 going to do? That's just going to move everything up 2 units. So what's that going to do? Well, if we move everything up 2 units, minus 1/2 plus 2, that's 1.5. 1/2 plus 2 is 2.5. 0, which is the x-axis, that's a 2. Other than that, everything stays the same. We have pi over 15, 2 pi over 5 plus pi over 15. I'll put a dotted line here because we'll start at 2, go up to 2. Oh, I forgot to divide my period into fourth. Up to 2.5, down to 2, down to 1.5, up to 2. And there's our graph. And then it just repeats, going left and right. Great. And so that gives us what adding or constant does. If we subtracted a 2, it would push it down 2 units. So to summarize all of that, how to graph a equals sine bx plus c. A is the amplitude, right? And that's up and down from the x-axis. So the range of the function is from minus a to a. B and C control the frequency, how many cycles in 2 pi, that's B, and the phase shift, and that's minus C over B. So if you start with a function whose period is 2 pi, you take the thing inside the sine, put it in the middle, and then try and solve that for x. That'll give you the frequency and the phase shift. This is where the cycle, the x value where the cycle starts. Okay, so that's how we can graph a sine bx plus c. It requires a little practice. It seems like a lot of stuff, but if you practice it, it's not too bad. Remember that a is the amplitude, bx plus c, set it up like that, and you can get the frequency and the phase shift. So how can you get a, b, and c from the graph of y equals a sine bx plus c? So here's the graph of y equals a sine bx plus c. We don't know what a is. We do know that, because they tell us, this is minus pi over 8. And it helps to remember that 2 pi is about 6.28, about 6.3. So what's a, b, and c? A is easiest to find. Right? The maximum of this function is 2. Min equals minus 2. Minimum is the lowest point on the graph. So our amplitude A equals 2. So that's nice. A doesn't have anything to do with either B or C, right? But B and C are a little bit commingled because together they give you the phase shift. So if 2 pi is 6.28, how many cycles do we have in 2 pi? Well, if we're starting here, 2 pi, this looks like it's about 0.2, 0.4 minus 0.4. So 2 pi plus 2 pi minus 0.4 is going to be about, what, 5 point, if it's 6.28 minus 0.4, 5.88. So if we start here and we look for 5.88, that'll be around here. So right there. This distance, that's 2 pi. Because we just started at this point and looked how far to the right is 6.28. So 1 cycle, 2 cycles, 2 complete cycles. So B equals 2. Great. How do we find C? Well, I would just say, well, how do we actually find out what C is? Well, you put 2x plus C, because we know that B is 2. Right? So we take bx plus C, and we put it between 0 and 2 pi. We know B is 2, so we can plug that in for that. Now to find out what C is, we subtract minus C is less than or equal to 2x is less than or equal to 2 pi minus C. Divide everything by 2, minus C over 2 is less than or equal to x is less than or equal to 2 pi over 2 minus C over 2. And the thing to remember is this number where the cycle starts. So minus C over 2 should be equal to minus pi over 8, because minus pi over 8, that's where our cycle started. So multiply both sides by minus 2, C equals pi over 4. And so our function is y equals, then we go over here, y equals 2, because that's A, sine 2x plus pi over 4 because we calculated c to be pi over 4. And that gives us our graph. So if I know where the graph, if I have a picture of the graph, the amplitude is just how high up and down it goes. B is how many you can fit into 2 pi, how many cycles you fit into 2 pi. And then the point where you start is minus b over c. And once we minus c over b, and if you know b, then you can find c. Okay, so that tells us how to deal with sine. What about the other trig functions? What about cosine? Well, this is the same kind of deal. We can build the graph of y equals cosine x the same way we build the graph of y sine x. So cosine x on the unit circle is the x coordinate of an angle. So if we start with x equal to 0, an angle of 0, here, and that x coordinate is 1. An angle of pi over 2 is this angle. There, at that point, our x coordinate is 0. Angle of pi, that brings us 180 degrees. Out here, our x coordinate is minus 1. 3 pi over 2 brings me down to the negative y-axis, and there my x-coordinate is 0. And a full cycle of 2 pi brings me back to an x-coordinate of 1. So a full cycle of cosine, maximum is 1, minimum is minus 1. But here we, and we start with 2 pi as one cycle. Cut it in half, cut in those in half, so we have quarters. This is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi. So cosine starts positive, 0, negative, 0, positive. Like that. And then if you go out to 4 pi, same deal, you cut it in half, cut each of those halves in half. Positive, 0, negative, 0, positive. Slightly different pattern than sine, and it continues off to the left. So there's our basic graph of sine of x. So again, well, that's what I just did, the 5 special points. That's these. Zero comma 1 is here, pi over 2 comma 0 is there, pi comma minus 1 is down here, 3 pi over 2 comma 0 is there, and then 2 pi comma 1 is up here. So there's our 5 special points on the graph. So basic properties of the graph of cosine: domain is all reals, the range is minus 1 to 1, the period is 2 pi. It's an even function, right? So if we, I'll take this space to graph my cosine. Right, 2 pi, pi over 2, 3 pi over 2. One, minus 1 in the y-axis. Positive, 0, negative, 0, positive. And if we go to negative 2 pi, we get the same things. And we're running left to right, that would take positive, 0, negative, 0, positive. So my graph is one cycle there and one cycle there. And you see that it's a reflection over the y-axis. So it's an even function. And then finally, the 5 special points are listed down here. So can we graph a cosine bx plus c the same way we graph y equals a sine bx plus c? Yep, and it's exactly the same procedure. So for this, the amplitude equals 2, period, and phase shift 0 less than equal to pi x minus pi over 4 less than equal to 2 pi. So we add a pi over 4 everywhere. We get pi over 4 here, less than equal to pi x, less than equal to 2 pi. And then we divide each side by pi. And if I do that, I get 1/4 less than equal to x, less than equal to 2. Oh, I forgot to add the pi over 4 over here. There we go, plus 1/4. So length of the period is 2. And we start at 1/4. So what's our graph going to, oh, amplitude is 2, keep that in mind. So this is y equals 2 cosine pi x minus pi over 4. So what's our graph going to look like? Well, here's my y-axis, here's my x-axis. We're starting at 1/4, that's here. And then we're going to go to 2 plus 1/4. And how do we sketch that? Cut this in half, cut this in half, cut this in half. Put in my amplitude, which is from 2 to -2. So that's my amplitude. What does cosine do? Positive, 0, negative, positive, 0, positive. So one cycle of cosine will look like that. So that's that graph. And then it can continue, right? Period is 2, so this would be 4 plus 1/4 if we just added 2 to this. Cut it in half, cut it in half, cut it in half. Positive, 0, negative, 0, positive. There's our graph. And if we go back this way, we get -2 plus 1/4. If we subtract 2 from that, cut it in half, cut those in half. Positive, 0, negative, positive, 0, positive. And there's our graph of y equals 2 cosine pi x minus pi over 4. And it just continues like that all the way out. How do we get the graph of y equals a cosine x? A secant bx plus c from the graph of y equals a cosine bx plus c. This is actually surprisingly easy. There's a little blue line under here because Word thinks I should do something else than write, actually surprisingly. But secant of x is 1 over cosine x, so graph a cosine bx and invert it. So what's the graph of this look like? Well, we'll start with our graph of y equals 2 cosine pi x minus pi over 4, which we just graphed above. So I'm going to put that down here so I have enough space. It started at 1/4, went to 2 1/4. Amplitude was 2. How do we graph that? Cut this in half, cut this in half, cut this in half. Positive, 0, negative, 0, positive. So there's one cycle of 2. So what does, oh, there should be parentheses there. Y, oh, and I should put that there because I'm going to draw there. Y equals 2 secant pi x minus pi over 4 looks like. Well, it'll start here. As this gets smaller, right? 1 over that gets bigger, right? Because secant is 1 over cosine. So if we take these outputs and we take 1 over them, they just get bigger and bigger and bigger. So I'm going to put a dashed line here. If I think about my y coordinates here, right? The y coordinate here, say, is 1. So if the y coordinates are decreasing here, 1 over the y coordinates are actually going to be increasing. So we're going to end up going up. And as we get closer and closer to here, my y coordinate is getting closer and closer to 0, which means this is actually going up to plus infinity. And I start here. What's my graph going to do? For 2 secant pi x over 4, as my y values, as I go this way up the graph of cosine, the y values get closer and closer to 0. So 1 over the y values get bigger and bigger and bigger, but they're negative. So they go down like that. And I'll put in a graph here. Right. This continues on. Right. So the graph of secant, every time you've got a 0, an x-intercept for your cosine function, you'll have a vertical asymptote for your secant. The secant will come down, touch it at the maximum, and just go back up. If your graph is below the x-axis, you still have vertical asymptotes, and the graph of your secant will come up to touch that and go back down. So these things with the asymptotes, those are the graphs of secant. So everywhere cosine graph has an x-intercept, the secant graph has a vertical asymptote. Okay. Can you get the graph of cosecant from the graph of sine the same way? Yes. Right? Because sine and cosecant is the reciprocal of sine. So cosecant is vertical asymptotes where sine has x-intercepts. So I'm not going to actually do an example of cosecant. What about tangent? Tangent and cotangent. These are different from the other ones. So how do we go from the unit circle to the graph of tangent? Well, we have to think about what tangent is in the unit circle. So how did we define tangent? Well, if I call this point A comma B, so this is A and this is B, then tangent, and I'll call the angle X. Tangent of X is opposite over adjacent, so that's B over A. Well, what is that? It's the slope of this line, right? Change in y over change in x, so b over a is the slope of the line. So the graph of the tangent is the graph of the slope of this radius as we go around the circle. So x, tangent of x. With 0, that means we're right here, right? And our y is 0, right? It's a horizontal line, so it's got slope 0. If we're at pi over 4, well, we know from a 45, 45, 90 triangle that a and b are actually exactly the same, so our slope is going to be 1. And if we get to pi over 2, we know about that is the slope of a vertical line is undefined. So tangent is undefined. It's going to have a vertical asymptote at pi over 2. We can go the other way. Minus pi over 4 is down here. And that's, again, a 45, 45, 90 triangle. But my sine is negative. So actually, this is going to be negative 1. So minus pi over 4 has slope negative 1, because if you think about this line going down for y, so that's going to be negative. And minus pi over 2, right? The slope of this line is undefined. Now we can also do what happens if we keep going. So if we look at 3 pi over 4, right, that's this angle. So 3 pi over 4. But that's actually the same line as we got for minus pi over 4, right? So that's going to be minus 1 as well. So what we find here is actually two angles that are separated by 180 degrees like that. They'll have the same tangent. And 180 degrees is pi, have same tangent. What's the upshot of that? Period of tangent and cotangent is pi. The other four, sine, cosine, secant, cosecant, have periods of 2 pi, but tangent and cotangent have period of pi, because we're just looking at these slopes of the line, and they repeat every 180 degrees. So that gives us 5 special points, and we'll label them again. X, tangent of x, minus pi over 2, undefined, minus pi over 4 was minus 1, 0 is 0, pi over 4 is 1, pi over 2 is undefined. So what's our graph look like? One cycle of tangent goes from minus pi over 2 to pi over 2, which is again a little different from sines and cosines because those went from 0 to 2 pi, but here we're doing minus pi over 2 to pi over 2. 0 is right there, right? But the procedure otherwise is the same. You take this, cut it in half, cut it in half, cut it in half. This is 0. This is pi over 4. This is minus pi over 4. Goes through 0, 0, goes through 1, and then it's got a vertical asymptote at pi over 2. Going to the left, minus pi over 4, it's minus 1, and then it's got a vertical asymptote at pi over 2, because these are horizontal, vertical lines there. So down, through 0, and back up. And it repeats. So if we go 3 pi over 2, which is pi plus pi over 2, cut it in half. 1, minus 1, 0. Vertical asymptote up through 0 to 1 and up. So there's tangent. And we can go the same way negative. Cut this in half, cut this in half, cut this in half. I'd have 1 here, 0, minus 1. Vertical asymptote there. Up. The other asymptote. This is an odd function. Because if you pick a point here and a point here, they're symmetric about the origin, right? And this point here and this point here, they're symmetric about the origin. So it's an odd function. And it has a period of pi, not 2 pi. So what are the 5 special points? Oh, again, these are 5 special points. 2 of them are asymptotes, so you have to keep track of that. Okay, basic properties of the graph of tangent of x. Domain is all reals except for these asymptotes. The range is all reals. It goes up to positive infinity, down to minus infinity. Period is pi, unlike sine, cosine, secant, cosecant, which all have period 2 pi. It's an odd function, and there's these 5 special points, including these 2 asymptotes. So can we graph y equals a tangent bx plus c the same way we graphed y equals, oh, this should be tangent, that's a cut and paste error, sine bx plus c. Same procedure, except you got to keep in mind that they don't really have amplitudes because they go up to plus or minus infinity already anyway. So what's the graph of this going to look like? So for tangent, the basic period is between minus pi over 2 and pi over 2. So let me I should have written that here first. Y equals tangent of x has period minus pi over 2 less than x, less than or equal to x, less than or equal to pi over 2. So how do we figure out what the frequency is and what the phase shift is here? Well, we take the thing inside the tangent and you plug it in for x and then solve this for x. So we're going to add a pi over 6 to both sides, minus 2 over 2, minus pi over 2, minus pi over 6. I'm actually not adding it, I'm subtracting it. And then to get rid of this 3, I'm just going to multiply 3 by 3. And that gives me minus 3 pi over 2, minus 3 pi over 6. And that should be a 2, not a 3. Is less than or equal to x is less than or equal to 3 pi over 2 minus 3 pi over 6. And we can tidy that up a little bit to say that this is minus 3 pi over 2 minus pi over 2, right? That's 3 pi over 6 is less than or equal to x is less than or equal to 3 pi over 2 minus pi over 2. Okay, so what's the length of my cycle? It's the distance between these 2 points. So minus 3 pi over 2 to 3 pi over 2, that means my length of my cycle is 6 pi over 2. So take this minus that for tangent, and that gives you the length of your cycle. Where does it start? Well, that's still this thing. It starts at pi over 2. So what's my graph look like? It's going to start at minus pi over 2. And then it's going to go for a cycle of 2 pi. So it'll go from, oh, that's not right. What did I do? So actually, the length is that we're actually starting it at minus 3 pi over 2 minus pi over 2, which is minus 4 pi over 2, which is minus 2 pi. And then this is to minus pi. Oh, if I knew how to do division, I would be much happier. Okay, so 6 divided by 2 is not 2. 6 divided by 2 is 3. So I'm less confused here. If we calculate this number, that's minus 2 pi. That's actually where we're starting. If we calculate this number, which is 3 pi over 2 minus pi over 2, that's 1 pi over 2. No, 3 pi over 2 minus pi over 2 is 2 pi over 2, which is 1 pi. We're actually starting at minus 2 pi. We'll be going to pi. How do we graph the function? Halfway in between, cut that in half, cut that in half. What does a cycle of pi look like? We start with a vertical asymptote, end with a vertical asymptote. Halfway in between, we're at 0. Our amplitude is 2, so at these quarter points, instead of being at 1, we'll be at 2 and minus 2. So this one will be at 2, this one will be at minus 2. And then the graph starts on one asymptote, goes up through the middle point, up to infinity and down to infinity that way. Length is 3 pi, so the next place would be at 4 pi. Cut this in half, cut this in half, cut this in half. We go through there, amplitude, the multiplier is 2, so we'll be at 2 at this quarter point and minus 2 at this quarter point, down to minus infinity through this point. Let me draw on my vertical asymptote, and up to positive infinity. And so that's our graph, right? And then there'll be another one here, another cycle going up like that, and it just repeats. How do you get a cotangent bx plus c from the graph of tangent? Well, tangent and cotangents are reciprocal, so if we know how to graph this function, 2 tangent x over 3 plus pi over 6, we can get the graph of cotangent. It'll have vertical asymptotes where the tangent has x-intercepts, and x-intercepts where tangent has vertical asymptotes, and it's decreasing wherever tangent is increasing. So actually, I'm going to sketch this pictures can get pretty messy, but I'm going to sketch in the cotangent here very briefly. So cotangent, well, no, I'm going to do it on a separate thing down here. So the skeleton for y, no, for y equals 2 tangent x over 3 plus pi over 6. The skeleton we had for that was that we went from minus 2 pi to pi. So from minus 2 pi to pi, that was a vertical asymptote for tangent, and this was a vertical asymptote for tangent. And this was a 0 was halfway in between. So for cotangent, right, and then there was another 0 here for tangent, and a vertical asymptote at 4 pi. So for cotangent, wherever there's a vertical asymptote, there'll be a 0, so that'll be cotangent. Whenever there's a 0, there'll be a vertical asymptote. What does cotangent do? Tangent, if you're going from left to right, goes up from one asymptote to the other. Cotangent, going from left to right, goes down. And so this is the graph of cotangent. So to get the graph of cotangent from tangent, replace all the vertical asymptotes with x-intercepts, all the x-intercepts with vertical asymptotes, and draw on your curves. It's the same shape, it's just going down instead of up. And then finally at the end, we have the picture of the graphs of all 6 trig functions, sine, cosine, right? So sine is 0, positive, 0, negative, positive. Cosecant, wherever sine has got a 0, cosecant has got an asymptote. And it comes down to touch sine. Sine would look like this. So cosecant sort of flipped up and down like that. Cosine, 1, 0, minus 1, 0, 1. We're drawing cosine in on the secant graph. It looks like this. So this is my graph of cosine, and secant has asymptotes. Oops, my graph of cosine should go through the x-axis here. Has asymptotes where cosine has got 0s, so here and here, and touches it where cosine has maximums. Here's tangent, right? 0 here, and a asymptote here, 0, asymptote, 0, asymptote. Pi over 2 is where tangent is got an asymptote, so cotangent has a 0. Tangent has an x-intercept at 0, so cotangent has a vertical asymptote there, and then cotangent goes down. And so that's the graph of the trig functions.